Hello and welcome to this video course covering the design principles of Scikit-Learn. In this video, I'm going to give a background to Scikit-Learn, its general design principles, and then I'm going to talk about estimators, predictors, and transformers, which are essential objects in order to understand and use Scikit-Learn efficiently. Then I'm going to demonstrate a neat function to create a test set, pipelines and model selection through Gridsearch. These functionalities are frequently used, and understanding them will enable you to create better machine learning models. Finally, I'm going to give the references that I based this presentation on and suggest some further reading for those interested in that. The code examples that I'm going to demonstrate are available at GitHub, and you can find the link in the video description. I encourage you to work through the code for a better understanding. With that said, we're ready to begin the course, so let's get started. Scikit-Learn is an open source machine learning library for Python. It has various algorithms for supervised learning such as classification and regression, and unsupervised learning such as clustering. Its first public release was in February 2010, and scientific toolboxes built around Scikit are called Scikits, hence the name Scikit-Learn. Scikit-Learn is widely used in commercial and academic settings, and it is designed to be simple, efficient, and usable to non-experts. Some important principles that the design of Scikit-Learn follows are the following. Consistency. All objects share a consistent interface and have a limited number of methods. The documentation is consistent as well. Inspection. Constructor parameters and learned parameters are stored and accessible as public attributes. Learned parameters are accessed by using an underscore suffix. Non-proliferation of classes. Only learning algorithms are represented using custom classes. Datasets are represented as NumPy arrays or SciPy sparse matrices. Hyperparameters are represented as regular Python strings or numbers whenever possible. Sensible defaults. When user-defined parameters are required, Scikit-Learn provides appropriate default values. This makes it easy to test and implement different models to get a baseline. One of my favorite properties of Scikit-Learn is the very well-written and consistent documentation. So in this example, I've searched for ridge regression in Scikit-Learn, and if I go to the web page for the documentation, then the first thing we see is the function parameters. Then we have a short description of the function, and then if you would like to check out more details, you can also look at the user guide. If you would like to check the source code of the function, you can do that here, but you probably won't do that so often. More details about the function parameters are available here. And if you continue down, we can also check out the attributes of the function. And continuing even further down, we have an example where the function is used, and this example is often very helpful in order to understand how to use the function. Then we have the function methods listed here. And if you would like to read more about the function methods, then they are available here. Finally, going to the bottom of the page, we have some complete examples using Scikit-Learn linear model ridge in this case. And as I said in the beginning, the documentation in Scikit-Learn is consistent. So if I go to another web page, and in this case search for polynomial futures Scikit-Learn, and then go to the documentation site, then we will see that the same pattern is arising. We have the parameters, description, user guide, parameters again, and so on. So the documentation in Scikit-Learn is often very helpful, and you should definitely make it a habit to read it. The central object in Scikit-Learn are estimators. Estimators that have a predict method are called predictors, and estimators that have a transform method are called transformers. Estimators are used to build and fit models, predictors are used for making predictions, and transformers are used for transforming data. We are going to cover each of them in more detail and also give a code demonstration. Estimators are initialized before they are fitted to learn from data. In the first step, we attach some hyperparameters to control the learning process, as I have done here, where I have set the hyperparameter fit_intercept equal to true. In the second step, we use the fit method where we run a learning algorithm for determining model-specific parameters based on the training data. These model-specific parameters are available as attributes on the estimator object and are accessed using an underscore suffix. So after I have fitted my model to the data, I can access learned parameters such as the intercept by using an underscore suffix. Estimators that can make predictions through the predict method are called predictors. Predictors must provide a score function which quantifies the quality of its predictions. And in Scikit-Learn, higher scores means it is better. So in this example, lindreg is now used as a predictor because we use the predict method. Now I will give a code demonstration of estimators and predictors. The first thing I do is to import some packages. Next, I generate some random data that I also plot. And then I'm importing the linear regression model from Scikit-Learn, and then I initialize it before I fit it to the data x and y in this case. If I would like to check out the hyperparameters and the corresponding default values in this case, then I can use the method getParams. If I would like to see learned parameters, then I can access them using an underscore suffix. So here I am printing out the intercept and the slope coefficient. Then I'm going to make some predictions, and in order to do that, I generate some new data. Then I'm using the predict method to make predictions. And then finally, I'm plotting the original data that I simulated and the predictions. And looking at the plot, we see that the model seems to be quite good. So this was a brief code demonstration of estimators and predictors, and I really encourage you to work with the code yourself to really learn this. Estimators that can transform a dataset through the transform method are called transformers. The transform method takes a dataset you want to transform as an argument and returns the transformed dataset. So in this example, I am first importing standard scaler, which standardizes futures to zero mean and unit variance. This is useful in some machine learning algorithms, such as support vector machines. Then I am instantiating a standard scaler, fitting it to the data x, and then finally transform the data x and assign the standardized dataset to the variable x transformed. There is a convenience function called fit_transform that simply combines the two steps, fit and transform, into one. Now I will give a code demonstration of transformers. First, I import some packages, Then I'm generating some random data that I also plot. Next, I manually calculate the mean and variance of the data and then print out the results. We see that the mean of the data is around 0.94 and the variance of the data is around 0.35. Then I am importing the standard scaler, initializing it before I fit it to the data, x in this case. After I have fitted my scaler to the data, I can access learned parameters by using an underscore suffix. So here I am printing out the learned parameters mean and variance, and we see that we get the results 0.94 and 0.35, which is exactly the results that we got above when we did the calculations manually. But you will notice that due to different number of decimals, the result is not exactly identical. After I have fitted my scaler, I can transform the x data, and then the transformed data I save in the variable x transformed. And printing out the mean and variance of the transformed data, we see that we basically get 0 and 1, just as expected, and that the results are not exactly 0 and 1, that's due to the computer not being exact. Finally, I demonstrate that I can combine the two steps of fitting and transforming into one by using the fit transform method. And if we use this method and then print out the results, we see that the results are exactly as when we did the fit and transform in 2 steps. A test set is often around 20% of your data, or less if it is a big data set, that is set aside and not used until you finish your supervised machine learning model. When finished with your model, evaluate it on the test set to get an estimate of your model's future performance. Generally speaking, good performance on the training set and bad on the test set indicates overfitting. In Scikit-Learn, it is easy to create a train and test set by using the function train test split. You can read the documentation for the details. In Scikit-Learn, the function Gridsearch CV, where CV stands for cross-validation, allows you to do an exhaustive search over specified parameter values for an estimator and then selects the best one by cross-validation. The best one in this case is decided based on a score function. For large hyperparameter spaces, the function randomized search CV can be useful, and if interested, check out the documentation for details. Now I will give a code demonstration of Gridsearch. First I do some imports. Then I load the iris dataset, which is a very famous dataset often used when demonstrating different machine learning models. Then I initialize a support vector classifier, specify a parameter grid that I want to check in my grid search later on. And here in the grid search, I say that I want to look at the support vector classifier model. I want to evaluate the following parameter grid, so param grid I defined here above. And then I want to do 5 cross validations. And then I fit my grid search, and after I have fitted the grid search to the data, I can check which parameters are the best by looking at the best params attribute. And looking at the results, we see that the best model had C equal to 1 and a linear kernel. And because C is equal to 1 is the left endpoint, it might be worthwhile to try smaller values of C to check if we can get an even better model in the grid search. Finally, if we want to check out details about the grid search, we can use the CV results attribute. And looking at the results, we can here see different parameters that were evaluated. And if we scroll to the right, we see different test scores. And we have test score 0 up to 4, meaning that we have 5 test scores, and the reason for that is because we used 5 cross-validations. And then we can also check at the mean test score, and the highest score is 0.98 and it occurs in 2 places. This means that we have 2 models that have ranking equal to 1. And in the case of ties, Gridsearch will choose the first model, meaning that this model was chosen. So C equal to 1 with a linear kernel, which is also the result that we saw here. So the brief code demonstration of Gridsearch is now done, and as always I encourage you to work with the code yourself. In machine learning, data is often going through a sequence of transformations to, for instance, handle missing values and scale data. Through pipelines, we can chain these steps together so that they run sequentially. All estimators in a pipeline, except the last one, must be transformers, and the last estimator may be of any type. 2 benefits of pipelines. 1. Convenience and efficiency. You only have to call fit and predict once on your data to fit a whole sequence of estimators. 2. Joint parameter selection. You can grid search over parameters of all estimators in the pipeline at once. If you want to handle different columns such as numeric and categorical jointly, then you should use the function column transformer, and I strongly recommend you to read the documentation for details. Now we're going to look at pipelines. So in this example, we have an array that has some missing values. And if we compute the arithmetic mean along the columns and ignoring the missing values, we get the numbers 7, 5, and 4. The reason for this is, in the first column, for example, we have 4 plus 10, which is 14, and 14 divided by 2 is 7, and 7 is the first number. In Scikit-Learn, there is a very handy function called simple imputer. With simple imputer, you can easily handle missing values, or more specifically, you can replace missing values. So here I have specified the hyperparameter strategy to be equal to mean, and this means that the missing values are going to be replaced by the mean of the columns. So if I use the fit transform method of my simple imputer, we see that the first missing value is replaced by 7 because the mean of the first column was 7. Next, I can create some polynomial futures, and if I do that, I get the following result. Both of these steps can be combined into one step with a pipeline. So here I have named the first step missing values, and I'm using a simple imputer. And the second step I have named polynomial, and I'm creating polynomial futures. If you want to, you could name the steps something else. Finally, by using the fit transform method of the pipeline, we see that we get exactly the same results as we did before. So pipelines is a very strong tool that you definitely should have in your machine learning toolbox, so try out the code. In this video, I'm going to demonstrate how we can combine Gridsearch with a pipeline. So first we do some imports, then we generate some random data and make a scatter plot. Then I'm creating some new data that I called xnew, and we're going to try to predict this data xnew with 2 different models. In the first model, we have a pipeline where we create polynomial futures of degree 2, and then we create a ridge regression with alpha set to 1. So I fit this model to the data and then predict the data xnew. In the next model, we are going to choose the hyperparameters optimally by Gridsearch. So in order to do that, we first use the getParams method to check what hyperparameters we have and what they are called. So for example, we have poly_futures_degree. And we also have regression __ alpha. So here I'm specifying a parameter grid. I am fitting my grid search to the data, and then I am predicting the data x new. Finally, I am plotting the data that I simulated and the two models. The red model is the one chosen by Gridsearch, and the black model is the one chosen by setting hyperparameters basically arbitrarily. More specifically, the red line is the predictions that were done by the Gridsearch model, and the black line is the predictions that were done by the other model. And as you can see from this plot, the Gridsearch seems to be much better. So as demonstrated in this video, we can search through parameters of all estimators in a pipeline at once by using Gridsearch, and this is very powerful. This presentation is to a large extent based on the following two articles: Scikit-Learn, Machine Learning in Python by Pedregosa and co-authors, API Design for Machine Learning Software, Experiences from the Scikit-Learn project by Butnik and co-authors. Both of the articles were great, and I can recommend you to read them. If you would like to dig deeper into machine learning with Scikit-Learn, then one book that I really like and could recommend is Hands-on Machine Learning with Scikit-Learn, Keras and TensorFlow by the author Geron. At the homepage of Scikit-Learn, you can check out Getting Started, tutorial and the user guide to learn more. With that said, this is the end of this presentation. Thank you for watching. Bye.